What does it mean for something to be cold when nothing is there to feel it? In space, cold isn't a mood, it's motion, fading atoms slowing towards stillness. Some regions dip lower than anything on Earth, while a few quiet labs push even closer to the hard limit nature allows. At those edges, familiar rules bend just enough to surprise. Currents flow without resistance, fluids slip without friction, and time's everyday pace feels different only because processes stall. We'll move step by step through how we define temperature and why zero in physics is not the zero on your weather app. If calm, careful science helps you unwind, a light like and subscribe supports the work. Let's begin with the number line of cold. Cold can feel obvious, yet in science it has a clear meaning. It is not a substance or a force. It is the lack of heat. Heat comes from motion at the microscopic level. Every solid, liquid, or gas is built from atoms and molecules that move, vibrate, and collide. More motion means more thermal energy. We sense that as warmth. Less motion means less thermal energy. We sense that as cold. Temperature is a way to track that average microscopic energy. If we could zoom in on the air near your face or the liquid in a mug, we would see a constant shuffle of particles. They do not stop completely unless they reach absolute zero, the lowest temperature allowed by the laws of physics. Absolute zero is 0 Kelvin, which equals 273.15 degrees Celsius, or 459.67 degrees Fahrenheit. It is a limit we can approach, but not reach. There is always a little motion left. That limit helps set how scientists define temperature and why certain scales are more useful than others. Most people meet temperature through Celsius and Fahrenheit. In Celsius, pure water freezes at 0 degrees Celsius and boils at 100 degrees Celsius at standard pressure. The scale was designed around those points. In the United States, Fahrenheit is common. Water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. Daniel Fahrenheit built his scale in the early 1700s using mixtures of salt and water and an estimate of human body temperature. The choices were practical, not fundamental. Scientists often prefer Kelvin. The Kelvin scale starts at absolute zero and counts upward with degrees the same size as Celsius. Removing negative values makes it a direct measure of thermal energy. 0 K means no extractable thermal energy. Higher K means more. There are special experiments with negative temperature in a technical sense, but those systems are not colder than absolute zero. They are out of scope here and do not change the basic picture. Cold as we feel it depends on heat flow, not just the number on a thermometer. Heat flows from warm to cool through three main routes: conduction, direct contact; convection, moving air or liquid; and radiation, infrared light, leaving your skin. A room at 60 degrees Fahrenheit, about 16 degrees Celsius, feels different if the air is moving or still, dry or humid, if you sit on wood or on metal. Metal feels colder than wood at the same temperature because it pulls heat from your skin faster. It conducts heat better. Wind increases heat loss by sweeping away the warm air layer hugging your skin, which is why a windy 25 degrees Fahrenheit can feel worse than a calm 15 degrees Fahrenheit. The wind chill index is a way to express that extra heat loss as an equivalent temperature. Humid air can also make cold feel sharper because moisture improves heat transfer from your skin and reduces evaporation's warming effects, when your skin is damp. People do not experience the same cold the same way. Body size, circulation, age, health, medications, acclimatization, and clothing all matter. Fingers and toes complain first because they are small and far from the core. Blood vessels there constrict to conserve heat. Skin sensors report quick changes more than absolute values because they evolved for protection, not precision. Your hands can feel very cold while your core temperature remains stable. That mismatch is why comfort and safety are not identical. Extreme cold injures by damaging cells. If you touch dry ice solid carbon dioxide at 78.5 degrees Celsius or 109.3 degrees Fahrenheit, or bare metal in sub-freezing air, heat leaves your skin quickly. Water inside and between cells can freeze, expand, and tear membranes. Ice crystals have sharp edges that puncture structures. Frostbite and thermal burns can look similar under a microscope. Both disrupt cells, blood flow, and tissue integrity, just from opposite directions of temperature. Cold is also a practical tool. Lowering temperature slows chemical reactions and biological activity because molecules collide less often and with less energy. Food lasts longer in a refrigerator around 4 degrees Celsius or 40 degrees Fahrenheit, and much longer in a freezer at or below 18 degrees Celsius or 0 degrees Fahrenheit. Many vaccines and lab samples are stored colder still to protect sensitive molecules. Some require standard freezers, others ultra-cold freezers around 80 degrees Celsius or 112 degrees Fahrenheit, and certain materials are kept near liquid nitrogen temperatures, 196 degrees Celsius or 321 degrees Fahrenheit. For living cells, simple freezing is risky because ice crystals can shatter delicate structures. Cryopreservation uses special antifreeze-like chemicals, cryoprotectants, and careful cooling to avoid crystal formation, sometimes forming a glass-like solid in a process called vitrification. Even with these methods, thawing must be controlled, and not every tissue tolerates it. Everyday sensations of cold come from heat racing out of you into something cooler. Standing in winter air, holding a steel railing, sitting on a stone step all change the rate of heat flow. The physics is the same whether we talk about a hand on metal or a satellite in deep space. Energy moves along temperature differences until balance is reached. The direction is set by a broader rule called the second law of thermodynamics. Energy spreads out if nothing stops it. Heat flows from hotter to colder regions because there are more ways for energy to be distributed than to stay concentrated. It helps to place these ideas on a rough temperature map. At the fiery end, molten lava at many volcanoes is around 1,200 degrees Celsius, about 2,200 degrees Fahrenheit. The sun's visible surface is about 5,500 degrees Celsius, about 9,900 degrees Fahrenheit. Deeper inside, the core reaches roughly 15 million degrees Celsius, where hydrogen nuclei fuse into helium and release light and heat that eventually reach Earth. Those numbers show how much energy atoms can store when they move and collide with extreme intensity. Closer to everyday experience, a mild summer day might sit near 30 degrees Celsius, 86 degrees Fahrenheit. A comfortable room is about 20-22 degrees Celsius, 68-72 degrees Fahrenheit. The human body maintains a core near 37 degrees Celsius, 98.6 degrees Fahrenheit. Water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, and boils boils at 100 degrees Celsius, 212 degrees Fahrenheit, under standard pressure, landmarks that anchor our sense of warm and cold. Colder than most weather, Antarctica can reach below 70 degrees Celsius, 94 degrees Fahrenheit, in severe conditions, and the historical record has dipped even lower at high, dry sites. At 196 degrees Celsius, 321 degrees Fahrenheit, nitrogen becomes a liquid. Pour it on a flower, and the stiff, cooled cells can fracture like glass. Those demonstrations show how materials change behavior as thermal energy drops. Beyond Earth, the interplanetary and interstellar environment adds a new element. A vacuum has no air to carry heat by convection, and conduction needs contact. Objects in space gain and lose heat mainly by radiation. They absorb sunlight and emit infrared. Far from stars, the universe's background sets the equilibrium flaw. That background is the cosmic microwave background, a faint relic of the young universe at about 2.7 K, roughly 270.4 degrees Celsius, 454.8 degrees Fahrenheit. An object shielded from starlight and warmed only by that background will drift toward that temperature over time. It isn't absolute cold, but it is the lowest natural baseline. The path from hot to cold is continuous. As temperature falls, motion slows, and new behaviors emerge. Metals can carry current with almost no resistance below a critical temperature superconductivity. Certain liquids flow without friction when cold enough superfluidity. These are collective effects, many particles moving in coordinated ways that don't appear at higher temperatures. Nothing magical, just quantum rules taking over once random thermal jostling is small. Thinking of cold as less motion ties these scenes together. A thermometer doesn't judge comfort, it reports average energy, wind chill, humidity, and materials matter because they change how quickly energy leaves you. Freezers and cryogenic systems work because slowing motion slows change. Planets, spacecraft, and deep space dust settle to temperatures that reflect the balance between energy in and energy out. Even the faint glow from the early universe defines a baseline for objects drifting far from stars. From a fingertip on metal to the dark between galaxies, the story is the same. Temperature tracks motion. Cold names the lower end. The numbers shift with context, and heat transfer mechanisms change with environment, but the principle holds. As motion fades, reactions slow, materials reorganize, and new patterns take over. And beneath all naturally low temperatures, physics marks a limit we approach, but never reach the theoretical endpoint where thermal motion only ever tends towards zero. Compared with that 2.7 K background, there is a lower mark, but only as a limit, absolute zero. It sits at the bottom of the scale. 0 Kelvin, 273.15 degrees Celsius, 459.67 degrees Fahrenheit. It's the theoretical point where thermal motion is reduced as far as physics allows. No heat-driven vibration, no random atomic jiggling. It isn't found in nature in a perfect form, and it isn't a practical destination. It is a boundary that shows what no heat left to remove means in the simplest picture. The third law of thermodynamics explains why we can't cross that boundary. As a system cools and its disorder entropy falls, the energy that must be removed rises sharply. Each step closer to absolute zero takes more work than the last. This isn't about bigger refrigerators. It's built into how energy and order reside in matter. Cooling slows motion, but the steps get smaller and harder, bringing you ever nearer to the limit without touching it. Laboratories push toward that limit using tools that act directly on atoms. Laser cooling uses light tuned just below an atom's preferred absorption line. Atoms moving toward the beam see the light shifted into resonance and absorb it. Each absorption and re-emission robs a small bit of momentum. Over many cycles, a gas of atoms can be slowed and cooled by orders of magnitude. Magnetic and optical traps then hold the slow atoms in a small region, while evaporative cooling lets the most energetic atoms escape, so the remainder settle into a lower temperature. For solid materials and detectors, dilution refrigerators circulate two isotopes of helium through a series of chambers. Phase changes in the mixture soak up heat and pull temperatures down to the millikelvin range. At such extremes, familiar categories of matter give way to collective behavior. A Bose-Einstein condensate forms when a cloud of bosonic atoms is cooled so far that many occupy the same quantum state. The cloud acts in unison. Its waves line up, and the system behaves like a single object with shared properties. Superconductors show a related kind of order for electrons. Pairs of electrons move through a crystal without scattering, so electrical resistance drops to effectively zero. Liquid helium-4 enters a superfluid phase and flows without friction through narrow channels that would block ordinary fluids. None of this violates basic rules. The same laws of motion and energy apply. The difference is that thermal noise has weakened enough for subtle quantum effects to dominate. The Kelvin scale fits this picture because it counts upward from the physical lower bound. 1 Kelvin is the same size step as 1 degree Celsius, but starting at 0 removes the need for negative numbers in ordinary thermal problems. A gas at 300 K carries roughly 3 times the average thermal energy per particle as a similar gas at 100 K, so comparisons become straightforward. Celsius and Fahrenheit remain useful for daily life because people connect them to water's behavior and weather. Kelvin keeps the accounting clear when the subject is energy. Everyday rooms sit near 293 K, about 20 degrees Celsius, 68 degrees Fahrenheit, a narrow and comfortable band on a long scale. Human skin senses heat loss rather than temperature alone. Conduction, convection, and radiation share the load of carrying energy away. Materials, airflow, humidity, and clothing control the rate. This same physics scales up to spacecraft, telescope, cameras, and cryogenic tanks. Detectors that look for faint infrared light must be cooled, or their own glow would drown out the signal. Shielding, radiators aimed at deep space, and closed-cycle coolers hold instruments at stable low temperatures so small signals can be measured with confidence. The range of temperatures in the universe is wide. Lava flows near 1,200 degrees Celsius. The sun's surface is about 5,500 degrees Celsius. Its core climbs into tens of millions of degrees where fusion takes place. Between stars, most of space sits near the temperature of the cosmic microwave background, about 2.7 K, 270.45 degrees Celsius, 454.8 degrees Fahrenheit. That value comes from relic radiation left over from the early universe and acts as a baseline for empty regions. Local conditions can pull temperatures away from the baseline when gas expands, when starlight is blocked, or when radiation escapes more quickly than heat arrives. Against that backdrop sits a notable object in the southern sky, the Boomerang Nebula, about 5,000 light-years away in the direction of Centaurus. It is a planetary nebula, the outflow from a dying, sun-like star that has shed its outer layers. The term planetary is historical. Early telescopes made some of these shells look planet-like in size and shape. In reality, they are thin clouds lit by the central star as it evolves toward a compact white dwarf. What sets the Boomerang Nebula apart is its temperature. Measurements at sub-millimeter and millimeter wavelengths show gas so cold that estimates place it near 1K colder than the 2.7K of the microwave background. The route to such a low value is rapid, nearly unimpeded expansion. Gas thrown off by the central star races outward at hundreds of thousands of kilometers per hour. As the gas expands, it does work on its surroundings and cools. The process is similar in principle to how a gas cools in a refrigerator coil, or why compressed air from a can feels cold as it expands, though the scales here are astronomical. Cooling alone would not drop the temperature below the background if outside radiation simply streamed in and warmed the gas. The Boomerang Nebula avoids that outcome because its outflow is dense enough to act as a shield. Layers of gas absorb and scatter incoming radiation from the environment, creating an interior where heat input is limited, while expansion continues to carry energy away. Within that cocoon, temperatures can fall below the ambient background for a time. The result is a natural cryogenic environment produced by a common stellar process taken to an extreme rate. The structure of the nebula has been mapped with higher resolution images and interferometers. What looked like a two-lobed boomerang in early blurry views resolves into a more symmetric hourglass with narrow jets and broader wings. The shape records how gas left the star, denser along some directions, thinner along others, possibly guided by magnetic fields or by a companion star that shaped the outflow. The cold component sits within these flows, where expansion is fastest and outside heating is most effectively blocked. The conditions are temporary. As the shell moves farther from the star, it thins, shielding weakens, scattered light penetrates more easily, and the rate of adiabatic cooling drops as the pressure falls. Over thousands of years, the interior will warm toward the general background of space. The central star will continue its evolution, exposing its hot core and ionizing the surrounding gas, which will glow before dispersing further into the interstellar medium. The very low temperature is a phase in a longer sequence, not a permanent feature. Observations of the Boomerang Nebula help test basic physics in an environment that is difficult to build on Earth. The data tie together gas dynamics, radiative transfer, and thermodynamics in a thin, expanding shell. Spectral lines from molecules and atoms carry information about temperature, density, and speed. Line strengths and widths reveal how cooling competes with heating and how different parts of the flow move relative to one another. Models built from these measurements improve our understanding of how dying stars return material to space and how that material mixes with the wider galaxy. The numbers associated with the outflow highlight scale. Speeds reach hundreds of kilometers per second in the fastest regions. Mass loss proceeds over thousands of years as the star sheds a significant fraction of its outer layers. The column densities needed to block background radiation are high for a nebula, which explains why so few objects reach the same low temperatures. Many planetary nebulae expand more slowly or with less dense shells, so outside light warms their interiors more effectively. The link between rapid expansion and extreme cooling shows up in other settings, but not usually to this degree. In the upper atmospheres of planets, gas that expands and rises can cool and form clouds. In the jets of young stars, gas rushing into thin surroundings radiates heat and changes phase. In the Boomerang Nebula, the combination of a strong outflow and effective shielding against incoming radiation drives the thermometer lower than usual. The mechanism is the same family of processes that cool gases in engines and lab equipment, stretched across light years and powered by stellar evolution. Absolute zero remains a limit in this story as well. The gas in the boomerang does not freeze its motion entirely. It approaches a very low thermal energy state because the rate of expansion beats the supply of heating. Even at 1 K, quantum motion persists, and collisions still occur at a reduced pace. The measurements do not contradict the lower bound. They show that nature can approach it more closely than everyday experience suggests when the conditions align. Temperature scales help keep these comparisons clear. Saying the nebula's interior is about 1 K highlights how near the outflow comes to the physical lower bound. Quoting Celsius or Fahrenheit would bury that significance under large negative numbers. The same choice simplifies estimates of how long the gas stays shielded, how fast background radiation leaks in, and how energy is shared as the shell thins. The Boomerang Nebula also shows that cold is not the absence of activity. Low-temperature chemistry can still proceed through quantum tunneling, where particles cross barriers they couldn't at higher energies. Dust grains provide surfaces where atoms meet and bind. Even in a near-frozen shell, slow processes add up over long times. When the nebula warms, those products can seed later clouds and feed the mix from which new stars and planets form. Long-wavelength instruments are essential for this work. Sub-millimeter and millimeter telescopes pick up emission from cold dust and gas, and their own receivers are cooled so instrument noise doesn't swamp the signal. Interferometric arrays combine many dishes for sharper images, tracing temperature, density, and motion across the nebula. Each gain in sensitivity and resolution tightens models of expansion and cooling and shows how rare such extreme conditions are among dying stars. Placed in the wider temperature landscape, the Boomerang Nebula marks how far adiabatic expansion can cool gas when heating is screened. It anchors one end of the scale, much as stellar cores and supernova shocks anchor the other. The same thermodynamic rules apply across the range. Energy flows, entropy sets direction, and materials respond to structure and environment. Step back from this single object, and the next question is the backdrop itself. What baseline temperature does empty space provide when no starlight gets in? Before galaxies had shape and stars began steady burning, the universe was hot, thick, and bright. Matter and light mixed as a dense plasma, where free electrons scattered photons in every direction. Nothing traveled far without a bounce. As the universe expanded, it cooled. About 380,000 years after the Big Bang, conditions dropped enough for electrons to join protons and form neutral hydrogen. With fewer free charges, light no longer scattered constantly. Space turned transparent, and the first long trip for photons began. That ancient light is still here, the cosmic microwave background, or CMB. Microwave describes its long wavelength today. Expansion stretched once blew a light into the low-energy microwave band over more than 13 billion years. The CMB fills space nearly evenly, at about 2.725 Kelvin, roughly 270.45 degrees Celsius, 454.8 degrees Fahrenheit. It sets the practical baseline for empty regions of the universe. Absent unusual local conditions, temperatures drift toward that value because this radiation bath is everywhere and hard to block. You cannot see the CMB with your eyes, but sensitive radio receivers can. In the 1,960 seconds, two engineers at Bell Labs, Arno Penzias and Robert Wilson, found a persistent background signal while testing a horn antenna for satellite work. The signal did not go away when they changed direction, tuned electronics, or cleaned the equipment. It came from the sky itself. They had stumbled onto the CMB and helped confirm a key prediction of Big Bang cosmology. The discovery later earned a Nobel Prize because it tied theory to a measurable relic of the early universe. Uniform is not the same as perfect. When NASA's COBE satellite mapped the CMB in the early 1,990 seconds, it showed tiny temperature differences across the sky, anisotropies at roughly 1 part in 100,000. These ripples are crucial. Slightly warmer spots had a little more energy. Slightly cooler spots had a little more matter. Given time and gravity, those small differences grew into the large structures we see today: galaxies, clusters, and the web of gas between them. Later missions, including WMAP and Planck, sharpened the picture. The data let scientists estimate the age of the universe, measure how fast it expands, and test its overall geometry. The pattern of ripples also constrains how much ordinary matter, dark matter, and dark energy exist. The CMB is not just a temperature field. Its light is polarized, its waves tend to vibrate in preferred directions because of the way photons last scattered in the early plasma. By measuring that polarization, researchers probe details of early growth and look for faint signatures from gravitational waves that may have passed through the young universe. That search is hard because the signals are subtle, and dust within our own galaxy can mimic them. Yet each improvement in instruments narrows the possibilities and refines the models. Because the CMB comes from every direction, it sets a common background for everything that sits in space. Far from stars or warm dust, objects radiate energy and cool toward the CMB value. That is why empty intergalactic regions are close to 2.7 K. To get colder, a place must be shielded from outside radiation and must expand or otherwise lose energy faster than it gains it, as with the extreme outflow in the Boomerang Nebula. Otherwise, the background light steadily warms matter until balance is reached. Between stars in a galaxy, conditions vary. Much of interstellar space is thin and cold, with only a few atoms in a cubic centimeter. For comparison, air at sea level has about 10-19 molecules in the same volume. In such a sparse medium, you would not feel cold in the usual sense. There is too little matter to carry heat away by contact, yet the radiation field still matters. Left alone, a small object would slowly cool by radiating energy and settle toward a temperature set by the CMB plus any starlight and infrared glow from nearby dust. Some regions inside galaxies are colder than the average void, not because the background vanishes, but because dust blocks starlight and gas can radiate heat away efficiently. These are molecular clouds, large, dark structures made mostly of molecular hydrogen, H2, with helium and small amounts of other molecules, such as carbon monoxide, ammonia, and water. Dust grains of carbon and silicate mixed with ices add opacity. Temperatures in dense parts of these clouds can drop to about 10 K or lower. Shielding keeps ultraviolet light from breaking molecules apart, and cooling lines let energy escape as the gas radiates. Low temperature is not an accident here, it is essential. Warm gas resists compression because its internal pressure is high. Cold gas has less thermal pressure, so gravity can gain an advantage. Where enough mass gathers in a small volume, often within dense cores inside the larger cloud, collapse begins. As the core shrinks, it heats and eventually forms a protostar. In that later phase, temperatures climb and the object brightens, but the process starts in the chill, not in the heat. Cold conditions also help chemistry proceed. Slow-moving atoms and molecules are more likely to stick together on dust-grained surfaces and build more complex species, including organics that later appear in comet and planet-forming disks. We do not see these cold clouds in visible light because they absorb and scatter it. Instead, astronomers map them with radio and infrared observations. Carbon monoxide is often used as a tracer because it emits at frequencies we can detect, and its brightness loosely tracks the amount of H2 nearby. Infrared instruments reveal dust warmed slightly by starlight around the edges of clouds, and colder dust deeper inside. The Orion molecular cloud is a nearby example. It stretches across hundreds of light years and contains bright star-forming regions and long filaments of dense gas, where gravity is at work on many scales at once. The timescales are slow by human standards. A cloud may last for millions of years. Cores form, collapse, and in some cases fragment to make multiple stars. Outflows and radiation from newborn stars then push back on their surroundings, carving cavities and sending shock waves through nearby gas. These feedback processes heat and stir the cloud, but they do not erase the role of cold in the first steps. Without cooling to remove energy, and without dust to provide shade, gravity would have a much harder time gathering matter into new suns. The temperature numbers in these environments are small, yet their effects are large. At 10 K, the typical speed of a hydrogen molecule is only a few hundred meters per second, slow compared to the kilometers per second common in warmer gas. That reduction lowers pressure. Emission from molecules like CO and from fine structure lines of atoms such as carbon and oxygen carries energy away, keeping parts of the cloud from warming as they compress. Dust grains radiate in the far infrared, acting as tiny radiators that balance the energy budget. Even in the larger, lower density regions between clouds, cold shapes what we observe. Neutral hydrogen emits a faint line at 21 centimeters, which traces the structure of the galaxy's disk and spiral arms. Where gas cools more and becomes molecular, that 21 cm emission fades and molecular traces take over. The boundary between atomic and molecular gas often sits where dust shielding becomes strong enough to protect H2 from ultraviolet light. This transition zone marks where chemistry and cooling have shifted the balance of forms. The link from the early bright universe to these dark, cold reservoirs is direct. The CMB shows the initial tiny differences that gravity later amplified. The same physical rules that let the background cool as space stretched also allow clouds to shed heat as they compress. A common set of ideas, temperature, radiation, and the transfer of energy connects the first transparent sky to the quiet places where new stars now grow. Numbers keep the story consistent. The CMB's 2.725K sets a floor for empty space. Dense cores in molecular clouds cool to roughly 10 K. Near young stars, temperatures rise to tens or hundreds of Kelvin, while stellar interiors climb into the millions. Across that span, the logic holds. When energy escapes and heating is screened, temperatures fall. When energy is trapped and added faster than it leaves, temperatures rise. Instruments tuned to the right wavelengths make these cold regimes visible. Radio arrays combine many dishes to map CO and other molecules with fine detail. Space-based infrared observatories avoid Earth's own infrared glow to see faint emission from cold dust. Detectors themselves are cooled, so internal noise doesn't swamp weak signals. The instrument's temperature and the target's temperature are parts of the same conversation, both governed by how heat moves and how radiation fills space. Cold interstellar settings also preserve records. Ice mantles on dust grains trap molecules that would not survive in warmer gas. When a young star heats its surroundings, those ices sublimate and enrich the gas with complex species. Comets in forming systems can store a sample of that chemistry and later deliver it to new planets. Measured in Earth laboratories and compared with space spectra, these molecules outline pathways from simple atoms to the building blocks used by biology. The quiet of these regions is not emptiness. It is slow motion. Few particles, low energy, and long times allow delicate processes to play out. Hydrogen pairs form, carbon chains grow, and gravity gathers mass grain by grain. The CMB continues to bathe everything in a steady, low-temperature field, a reminder of the universe's hot start and long cooling. Cold space is neither an absolute nor a void of activity. It is an active setting with clear rules, shaping what forms and how it evolves while the wider cosmos carries on. At the heart of that setting is dust. The same grains that cool clouds also shield chemistry, setting the stage for what survives and what grows. Fragile molecules persist in space because the same dust that cools a cloud also shields it. Tiny grains of carbon and silicate mixed with ices soak up ultraviolet light and soften shock fronts, protecting molecules from high-energy photons and cosmic rays. Inside dense cores, temperatures fall so low that even common gases, such as carbon monoxide, freeze out onto grain surfaces. These icy coatings are not inert. They provide sites where atoms and simple molecules meet, hold, and react. A faint trickle of ultraviolet light, filtered and scattered by dust, still reaches the ices and drives chemistry. Laboratory studies that mimic these conditions show that mixed ices of water, carbon monoxide, carbon dioxide, methanol, and ammonia, when irradiated and then warmed, produce new products, including amino acids and other organics. Slow chemistry on cold dust prepares ingredients that later re-enter the gas or are locked into comets and planet-forming disks. Between galaxies, the story shifts from chemistry to scarcity. Intergalactic voids contain so little matter that clouds cannot gather and cool. Gravity there has little to work with. The temperature in these vast regions stays pinned near the 2.7 K, set by the cosmic microwave background. With so few atoms per cubic meter, collisions are rare, and radiative cooling is weak. Nothing like a molecular cloud forms, and the main process is the quiet exchange of energy with the background radiation. Even this emptiness matters. The contrast between cold, thin space and the concentrated energy of stars and galaxies sharpens structure across the universe. Cold defines a baseline. Against that baseline, heat stands out and flows. The shielding role of dust and the low temperature of dense gas are both essential for building complexity. At higher temperatures, collisions are too violent, and bonds break as fast as they form. In cold, shaded regions, atoms move slowly enough to stick. Hydrogen atoms find each other on grain surfaces and become molecular hydrogen. Carbon and oxygen combine in steps to make carbon monoxide and water. With time, more elaborate species appear: formaldehyde, formic acid, methanol, and precursors to amino acids. When nearby stars switch on, they warm the grains, release trapped molecules back to the gas, and feed the chemistry of young disks. Cold delays the rush and gives reactions the time they need. Some of the coldest places in the universe are not in space at all. They are inside laboratories designed to remove energy with precision. Near absolute zero, ordinary tools fail. You cannot just turn the thermostat down. Motion must be controlled at the level of single atoms. Laser cooling is a key step. Atoms absorb light at very specific frequencies. If a laser is tuned a little below that frequency, an atom moving toward the beam sees the light shifted into resonance. It absorbs a photon and gets a tiny push opposite its motion. After it re-emits the photon in a random direction, the backward push remains. Repeating this from multiple directions slows motion along all axes. In practice, 6 laser beams arranged in 3 pairs, plus a magnetic field that changes with position, create a magneto-optical trap, MOT, that damps motion and gathers atoms. Temperatures can drop to microkelvin millionths of a Kelvin above absolute zero. To go colder, experimenters use evaporative cooling. They hold the atoms in a magnetic or optical trap and slowly lower the trap depth. The most energetic atoms escape first, and the rest re-thermalize at a lower temperature. Cycle after cycle, the average energy falls. For solids and detectors, a different approach, dilution refrigeration, uses a mixture of helium-3 and helium-4. When helium-3 moves from a concentrated phase into a dilute phase at very low temperature, the process absorbs heat. Pumping on the mixture and controlling flows stepwise can reach millikelvin thousandths of a Kelvin and below. At these extremes, matter shows collective behavior. Bose-Einstein condensation occurs when many bosonic atoms share the same lowest energy quantum state. Instead of acting as separate particles, the cloud behaves like a single wave with a common phase. This state was predicted in the 1920 seconds and first produced in 1995 using rubidium atoms. The work by Eric Cornell and Carl Wieman in Colorado and by Wolfgang Ketteler at MIT demonstrated condensates and mapped their properties, leading to a Nobel Prize. Since then, condensates have been made from several elements, including sodium and potassium, and used to study precision waves, vortices, and tunneling. Ultra-cold research is not limited to tabletop systems. NASA's Cold Atom Laboratory, operating on the International Space Station since 2018, uses microgravity to keep atoms trapped longer and free from sag due to weight. The extra time improves measurements and allows new trap geometries. On Earth, arrays of lasers, optical lattices, create periodic light patterns that hold atoms at regularly spaced sites. With these tools, researchers simulate models of solids, measure fundamental constants, and test ideas about quantum phases and transport. Even when experiments do not reach the nano-Kelvin regime, cryogenic temperatures unlock important effects. Superconductors carry electrical current with zero resistance below a critical temperature. Some materials require liquid helium cooling, around 4.2 K, while high-temperature superconductors work with liquid nitrogen, 77 K. Superconducting magnets power MRI scanners and particle accelerators. Low-loss microwave circuits and superconducting qubits for quantum computing also rely on cryogenic stages to reduce noise. Superfluid helium provides friction-free flow used in specialized cooling and in studies of turbulence at quantum limits. These technologies depend on accurate thermometry. Near room temperature, a metal probe or a gas expansion thermometer is enough. At cryogenic levels, temperature is inferred from properties that vary predictably with energy. The spectrum of light absorbed or emitted by atoms, the voltage across a junction with a known energy gap, the noise in an electrical resistor, or the speed of expanding atomic clouds in time-of-flight images. Instead of reading a dial, researchers extract temperature from a fit to data, because heat at these scales is motion and distribution, not a number on a glass tube. None of the laboratory values occur naturally on Earth. The coldest, reliably measured surface air temperature recorded in Antarctica sits near 89 degrees Celsius, 128 degrees Fahrenheit, at Vostok Station, with even lower satellite-derived estimates over the high plateau during clear winter nights. Those are extreme for weather, but still far warmer than the boiling point of liquid nitrogen, 196 degrees Celsius, 77 K, and unimaginably warmer than microkelvin or nanokelvin, conditions in atomic traps. The gap is a reminder that ultra-cold states are not weather, they are engineered energy landscapes. Cold reveals rules rather than breaks them. Lower thermal energy reduces random motion, so underlying order can form. In superconductors, electrons pair and move without scattering. In superfluids, quantized vortices and frictionless flow emerge. In condensates, phase coherence spans the entire cloud. These are not exceptions to physics. They are the same equations seen in a quieter regime, where small effects are no longer drowned out by noise. Returning to space, the logic matches. Shielding plus cooling enables molecules to build up on dust. Later, heating releases them, and chemistry steps forward in warmer gas and in young disks. Comets store samples of this cold chemistry and deliver them to forming planets. The difference between a void at 2.7 K and a dense core at 10 K may look small, but it marks a change in pressure, shielding, and reaction rates that drives the path from atoms to complex molecules and from gas to stars. Instruments must match the temperatures of the targets. Telescopes that study cold dust and gas operate at infrared to millimeter wavelengths. Their detectors and optics are cooled so the instruments do not outshine the signal. Space observatories use sunshades, radiators aimed at deep space, and cryocoolers. Ground arrays place antennas at high, dry sites to reduce water vapor, which absorbs and heats at the relevant wavelengths. Calibration against known sources and careful modeling of the atmosphere turn faint signals into reliable maps of temperature and density. The same thermal ideas guide engineering far from the lab. Spacecraft radiate heat to hold stable temperatures against sunlight and shadow. Insulation and coatings control absorption and emission. Batteries and electronics have preferred ranges and need both heating and cooling as orbits pass from day to night. In every case, heat flows from warm to cool. Design is the art of choosing the paths and the rates. Cold is not a pause button. It is a regime where motion slows, collisions soften, and order can emerge. Chemistry proceeds on dust-grained surfaces, condensates develop a shared phase, and superconductors move charge without loss. As temperature falls, everyday agitation fades, and quantum rules shape behavior. In the lab, that change can be timed and quantified. In space, it's traced by faint radiation that records low energy and low noise. One of the clearest demonstrations comes from a familiar element that turns strange when nearly all thermal motion is gone. At a few Kelvin, liquid helium crosses a sharp boundary into a new phase, a superfluid. It behaves unlike ordinary liquids. Internal friction drops effectively to zero, so a ring of superfluid set rotating keeps its motion because there is no viscosity to convert flow into heat. the circulation isn't continuous in any amount either. Quantum rules allow only specific values, quantized vortices, so the flow remains organized and stable rather than fading away. Superfluid helium also shows film flow along surfaces. A thin layer can climb the walls of a container and spill over the rim. This is not a trick of pressure or a hidden leak. It is a consequence of the liquid's coherence. Many atoms share a single quantum state and move together. Because the motion is coordinated, the fluid can pass through small channels that would block a normal liquid. Helium is unusual in that it does not freeze at atmospheric pressure no matter how cold it gets. To make solid helium, you must apply pressure. That wide liquid range makes helium a good system for studying low-temperature physics with clear signals. A related low-temperature phenomenon appears in conductors. In many materials, electrons scatter from atoms and imperfections and lose energy as heat. Below a critical temperature, certain materials enter the superconducting state. Electrons bind in pairs called Cooper pairs. These pairs move through the crystal in a coordinated way and avoid the scattering that causes resistance. Electrical resistance drops to zero within measurement limits, so a current can circulate for a very long time without fading. Superconductors expel magnetic fields when they transition, an effect called the Meissner effect. In Type II superconductors, magnetic field lines thread the material as organized filaments. Pinning of these filaments can lock a magnet in place above a superconductor and make stable levitation demonstrations possible. Superconductivity underpins familiar and emerging technologies. Medical MRI scanners rely on superconducting coils to generate strong, stable magnetic fields. Particle accelerators use similar coils to steer beams. Low-noise circuits and many designs for quantum bits operate inside cryogenic systems, where thermal motion is small and coherence lasts longer. Traditional superconductors require liquid helium temperatures. Some ceramic compounds become superconducting at higher temperatures that liquid nitrogen can reach. Other families only show high critical temperatures under extreme pressures, where structure and bonding change. The search for materials that retain superconductivity under more practical conditions continues because near-lossless transmission and compact magnets would have wide impact. Extreme cold supports quantum coherence in more general ways. At room temperature, random motion continually disturbs delicate quantum states. Small interactions with the environment scramble phases and push systems back toward classical behavior. Cooling reduces those disturbances. Tunneling through energy barriers becomes easier to detect. Interference patterns last longer. Atoms in engineered traps can occupy superpositions of states for times long enough to measure and control. This is essential for quantum sensors and quantum computers. The aim is not to change the rules of physics, but to reduce background noise so the rules can be applied cleanly. Order tends to appear as temperature falls because thermal agitation no longer overwhelms weak organizing effects. In liquids with the right interactions, atoms form a shared phase. In superconductors, electrons pair and move collectively. In magnets, spins align and form domains. These transitions are not arbitrary. They occur at specific conditions where energy and entropy trade places in the balance. The result is not strange behavior, so much as a clearer view of what the underlying interactions prefer when they are not drowned out by heat. Absolute zero sets the lower bound for all of this, and it remains unreachable. The third law of thermodynamics states that as a system approaches absolute zero, its entropy approaches a constant minimum. It also implies that reaching zero temperature exactly would require an infinite number of cooling steps or infinite time. Cooling becomes progressively harder the closer you get. Each fraction of a Kelvin removed demands more control and yields smaller changes. Thermal links carry less heat when the temperature difference shrinks. Pumps, fields, and lasers do real work, yet the returns diminish. Quantum mechanics sets another limit. The uncertainty principle forbids a state where both position and momentum are exactly known. If every atom sat perfectly still at a precise location, both quantities would be fixed at once. Instead, even when thermal energy is nearly gone, a small residual motion, zero-point motion, remains. This does not prevent very low temperatures. It prevents complete stillness. The main cooling methods each carry trade-offs. Laser cooling reduces the motion of dilute gases by stealing momentum one photon at a time, but it depends on specific atomic transitions and reaches limits set by the properties of the light and atom. Evaporative cooling lowers temperature by letting the most energetic atoms escape from a trap, after which the remainder re-thermalize colder. As the sample cools, fewer hot atoms are left to remove, and the process slows. Adiabatic demagnetization cools magnetic materials by first aligning their spins in a strong field while connected to a heatsink, then isolating the system and reducing the field. As the spins disorder without exchanging heat, the material's temperature drops. The method is powerful, but still bounded by the third law. Repeated cycles move you closer to zero, never to zero. Heat must always be carried somewhere else. Refrigerators, from kitchen units to dilution systems, work by transferring energy from the target to a working fluid and then rejecting that energy at a higher temperature stage. When the working fluid and the target become nearly the same temperature, the flow of heat slows. Thermal contact, surface area, and timing are all engineered to stretch performance, but the basic gradients still set the pace. Near the end, removing one more microkelvin can take many hours of careful control. These limits do not reduce the value of ultra-cold work. They define it. Within these boundaries, systems reveal features that ordinary conditions hide. Superfluids carry flow around obstacles. Their vortices form regular arrays that can be imaged and counted. Superconductors trap magnetic flux in precise amounts. The quantization shows up in sensitive devices called squids that measure magnetic fields far weaker than Earth's field. Ultra-cold atoms in optical lattices act as clean model systems for solid-state physics. By adjusting laser intensities and magnetic fields, researchers tune interactions and watch phases appear and vanish. Time plays a special role because lowering temperature often lengthens the timescales over which order persists. Coherence times stretch, allowing weak forces to accumulate measurable effects. Frequency standards built from cold atoms yield clocks of extraordinary stability. Interferometers using matter waves detect tiny accelerations and rotations. Such devices depend on the same fact. When random motion is quiet, phase relationships stay intact long enough to read. The deeper lesson from near-zero physics is that emergence and simplicity often go together at low energy. Equations that are hard to solve in their full microscopic detail can produce clean, macroscopic rules when fluctuations are small. Zero resistance, quantized circulation, and fixed flux packets are all examples of simple outcomes from many-body complexity. They are reliable precisely because temperature has been pushed low enough to suppress competing processes. Superfluid helium and superconductors also show how geometry and confinement matter. Flow in a ring differs from flow in a straight channel because boundaries control available states. Persistent currents in a loop survive because there is no easy way to change the quantized circulation without a disturbance large enough to create or destroy vortices. In thin films and nanowires, fluctuations are stronger and can disrupt order more easily, so critical temperatures and behaviors shift with size. Practical systems must account for thermal noise at every stage. Cables, supports, and measurement leads bring heat into cold regions if not designed carefully. Radiation from warmer parts of a setup can warm a target unless blocked or absorbed by shields. Vibration can convert mechanical energy into heat and disturb delicate states. Low-temperature experiments look simple from the outside, a few shiny metal cans and vacuum lines, but each detail manages a channel through which energy might creep back in. The same considerations echo in astrophysical settings. In dense interstellar cores, shielding and radiative cooling are the gatekeepers that let gravity compress gas. In young planetary systems, shadowed regions in disks protect ices and organics until heating later releases them. In neutron stars, temperatures fall to where superfluid neutrons and superconducting protons likely shape how the interior carries heat and magnetic fields. Across these scales, the pattern repeats. When energy can leave and disturbances are low, ordered states form and control behavior. Understanding why absolute zero remains a limit clarifies why the physics near it is so informative. The closer systems get to that limit, the fewer variables dominate. Thermal agitation fades, and small interactions become visible. The third law and quantum uncertainty do not block discovery. They define the ground on which measurements make sense. Each technique, optical cooling, evaporative steps, magnetic methods, dilution stages, moves energy along lawful paths and exposes the system to view. When temperature drops and random motion recedes, helium's superfluid phase provides a clear example. Its viscosity becomes so small that flow through narrow pores is effectively unimpeded. Heat moves in unusual ways, carried by coordinated excitations rather than by ordinary diffusion. Disturbances form quantized vortices instead of broad swirls, and those vortices interact and organize. Measurements of these patterns test ideas about turbulence at quantum limits and connect microscopic rules to macroscopic flow. Scientists have chilled atoms to within billionths of a Kelvin of absolute zero. At those temperatures, motion slows so much that many atoms act together as one system. Bose-Einstein condensates form when a cloud of bosonic atoms shares a single quantum state. The behavior is not a curiosity. It gives a clean view of quantum rules that are otherwise hidden by thermal noise. Near this limit, weak forces and small energy shifts become measurable. Interactions that are washed out at room temperature stand out in long, quiet measurements. That is why ultra-cold work matters for basic physics and for tools like precision sensors, superconducting circuits, and experimental platforms for quantum computing. Absolute zero itself remains a boundary. The third law of thermodynamics tells us that cooling gets harder the closer we come to the limit, and that reaching 0K would take an infinite sequence of steps. Quantum mechanics adds its own flaw. Zero-point motion means particles never sit in exact stillness. The value of the pursuit is not in touching zero, but in approaching it far enough that subtle effects dominate. Each improvement in cooling sharpens instruments, lengthens coherence times, and exposes structure inside matter that heat usually hides. Deep space is cold by everyday standards, but the way heat moves there is different from a winter night on Earth. In vacuum, there is almost nothing to conduct or convect heat. Objects cool, mainly by radiating infrared light. A bare object does not flash freeze in space. It leaks energy to the sky at a rate set by its temperature and surface properties. Spacecraft design is therefore a balance. Electronics and batteries must stay warm enough to work, while sensitive detectors must stay cool to avoid self-glow. The problem is managed with careful insulation, controlled heat paths, and, when needed, internal heat sources. Multi-layer insulation is common on satellites and suits. Thin, reflective films separated by spacers reduce radiative exchange between a warm surface and cold space. The layers act like a very light thermal blanket by reflecting infrared light back and by cutting down the view to cold surroundings. Inside, electronics produce waste heat. Heat pipes and conductive straps move that heat from where it is made to where it is needed, or to radiators that shed the excess to space. Components with narrow temperature limits are tied to stable stages with heaters that make small corrections rather than large swings. Far from the sun, sunlight is too weak for solar arrays and for passive warming. Radioisotope thermoelectric generators solve both problems at once. A pellet of plutonium-238 produces steady heat as it decays. Thermocouples turn part of that heat into electricity. The rest keeps systems above their minimum temperatures. There are no pumps or moving parts. Voyager 1 and Voyager 2 continue to operate decades after launch because their RTGs still provide power and warmth as they cross into interstellar space, where solar power would be ineffective. Cassini carried an RTG at Saturn for the same reason. At roughly 9-10 astronomical units, sunlight is only about 1% of the intensity at Earth. Some missions aim for cold, not warmth. Infrared telescopes need their optics and detectors colder than their targets, or their own heat will mask faint signals. The James Webb Space Telescope achieves this by staying in deep shadow behind a 5-layer sunshield, and by using radiators and an active cryocooler. Most of the observatory cools passively to about 40 K. Its mid-infrared instrument is driven lower, to around 7 K, so its detector noise stays below the sky signal. Keeping large structures aligned while they cool required careful choice of materials with low thermal expansion and a deployment plan that managed stresses as temperatures fell. Materials and lubricants behave differently in cold vacuum. Common greases can thicken or outgas. Mechanisms use dry lubricants such as molybdenum disulfide or graphite, or rely on solid-state flexures that bend without sliding parts. Wires and harnesses are built to stay flexible over large temperature swings. Thermal cycles during testing reveal weak points before flight. Thermal vacuum chambers expose spacecraft to heating and cooling in vacuum while instruments run. Radiators, heaters, thermostats, and control logic are tuned to keep each unit inside its limits as the craft rotates or passes through shadow. Space can still surprise. Early in a mission, sunlight angles and self-heating may differ from models by enough to push temperatures out of range. Control software is adjusted, heater set points are changed, or operating schedules are shifted to keep the system steady. Over time, stable, cold is an ally. Without air and weather, mirrors and detectors can hold calibration for years. Surfaces do not rust, components drift slowly. Long exposure to quiet conditions makes precision astronomy possible. The thermal story in space includes preservation. The same vacuum that chills also protects. Coatings last. Metals do not oxidize. The golden records on Voyager will remain legible far longer in interstellar space than any object left outdoors on Earth. At the same time, cold can challenge survival. Batteries lose capacity when chilled. Some alloys become brittle. Thermal gradients can warp structures. Design traits weigh these effects against science goals and power budgets. Engineers use the same basic physics that governs kitchen ovens and household insulation, applied with different tools. Heat flows from warm to cool by conduction, convection, and radiation. In vacuum, only conduction through structures and radiation matter. If a component must be warm, it is insulated and given a small heater. If a component must be cold, it is shaded and tied to a radiator. The balance changes with distance from the sun and with pointing. A slow-spinning craft may see large day-night differences. A fast-spinning craft averages them out. Keeping temperature stable also reduces mechanical drift. Mirrors hold focus. Antennas hold alignment. Clocks and oscillators behave more predictably when their environment is steady. Thermal control is therefore a foundation for guidance, communications, and timing, as well as for science. The simplest parts, blankets, shields, radiators, enable the most delicate measurements by keeping instruments in their designed range. Extreme cold is not only an obstacle, it is also a measurement tool. Instruments that look at faint infrared light must be colder than the signals they capture. Bolometers and infrared arrays are mounted on cold stages, so their dark current is low. Spectrometers measure tiny energy differences between lines only when their detector's thermal noise is suppressed. In particle physics, cryogenic stages reduce background events, so rare interactions can be seen. Across fields, cooling improves signal-to-noise by quieting the instrument as much as the environment will allow. Spacecraft that travel far must carry a thermal plan from launch to end of mission. During ascent, vehicles see aerodynamic heating and vibration. In orbit or on cruise, they see the cold of space and the heat of sunlight. Near planets, they pass through eclipses and bright reflections. Each phase has a thermal profile and a control strategy. The plan includes margins for aging, dust, and changes in surface properties. Over long missions, RTG power declines and heaters must be rationed. Teams reprioritize which instruments stay on and which enter hibernation, so vital systems remain within range. The same principles that protect instruments also make possible long-duration storage of materials in space. With adequate shielding from sunlight and internal heat sources, a sample container can coast near the background set by deep space. Thermal stability helps preserve fragile compounds for return. Sample return missions use passive and active cooling, plus fast transport, to keep temperatures within a narrow band. The cold of deep space shapes human systems as well. Life support must keep cabin air warm and remove moisture without wasting power. Spacesuits manage heat with reflective layers, active water loops, and heaters in gloves and boots. On the Moon or Mars, shadows can be far colder than Earth's poles, so rovers and habitats need robust thermal designs to survive night cycles. Energy budgets must cover heating, as well as mobility and communication. Deep cold also affects communications and power. Antenna electronics must stay within a tight temperature range to keep noise low and frequency stable. Solar panels lose output when coated with dust or when cooled too far below their design point, and their performance changes with temperature. Battery chemistry responds strongly to temperature. Heaters and insulation extend life and keep charge and discharge within safe limits. Radiation interacts with thermal control in subtle ways. High-energy particles can deposit heat in detectors or damage materials. Shielding adds mass and can change how heat flows. Designers trade between mass, protection, and thermal stability. Over time, cumulative effects of radiation can shift the properties of coatings and foams. Long-term missions plan for these drifts with calibration cycles and adjustable set points. The most distant machines we operate live in a steady, low-temperature bath. Their quiet warmth is deliberate. Inside the cold, carefully chosen heat sources keep clocks ticking and memory stable. Outside, blankets and shields face deep space. The contrast is intentional. A warm core, a cold shell, and a controlled path for energy to leave. The same logic runs from small CubeSats with simple heaters to flagships with multiple cryogenic stages. Instruments that demand even lower temperatures than passive cooling can provide dedicated cryocoolers. Mechanical coolers compress and expand a working gas in cycles that move heat from a cold tip to a radiator. They add vibration and complexity, so they are isolated and balanced to protect optics. The gain is access to temperature ranges otherwise unavailable in space for years at a time. Detectors tuned to these ranges can map the cold universe with clarity. Testing verifies models before flight. Thermal vacuum runs exercise heaters and sensors, while teams watch how temperatures settle and vary. Spin tests and lamp arrays simulate solar input from different angles. If a radiator runs too warm or a component runs too cold, blankets are adjusted, coatings are changed, or heater logic is rewritten. The goal is not perfection, it is predictable behavior within margins. Far from any star, a spacecraft's thermal story becomes simple to state and hard to execute. Hold what must be warm, cool what must be cold, and waste as little energy as possible. Achieving that with limited power is the craft. The same care that lets a telescope see faint galaxies also lets a probe wake from hibernation at the edge of the heliosphere and answer a call. There is a related idea often imagined for people rather than machines. If hardware can be kept stable for decades in deep cold, a natural question follows about biology and time. The concept appears often in plans for long journeys, where distance is measured in decades, and life support must bridge long stretches without sunlight or resupply. Stories make cryosleep look easy. Slide into a pod, press a button, wake up decades later as if no time passed. Real biology is less forgiving. Many animals slow their bodies in cold conditions. Wood frogs can freeze, pause a heartbeat through winter, then thaw and hop away. Some turtles, insects, and fish pull off similar tricks. They protect cells with natural antifreeze, control ice formation, and manage oxygen debt. Humans lack those built-in systems. Our cells hold a lot of water. Freezing water makes crystals that puncture membranes and tear tissue. That is not sleep, it is damage. Modern cryopreservation works around this by preventing ice. Tissues are cooled to very low temperatures, often near 196 degrees Celsius, 321 degrees Fahrenheit, the boiling point of liquid nitrogen. After adding cryoprotectants, chemicals that move into cells and reduce ice formation. With the right mixtures and timing, water can form a glass-like solid, a state called vitrification. In a vitrified state, structure is preserved and slow chemistry nearly stops. This already supports medicine. Sperm, eggs, embryos, and small tissue samples are stored for years and later used successfully. Some tissues, such as corneas and skin, can be banked for transplant. Size matters though. A thin slice cools evenly. A whole organ does not. Heat moves slowly through complex shapes. Parts overcool and crack while others lag and form ice. Rewarming is harder still. Warm too slowly, and ice can nucleate during the thaw. Warm too fast, and stresses fracture tissue. Research pushes at these limits. Teams test cryoprotectant blends with less toxicity, rapid warming with nanoparticles and radio frequency pulses, and perfusion methods that move solutions deep into organs. Vitrification of small animal organs has been reported with partial function after warming, but consistent, full-scale organ recovery remains unsolved. Scaling to an entire human body adds orders of magnitude in complexity, billions of cells, long delicate fibers, and a brain whose fine wiring encodes memory. A separate line of work studies deep hypothermia for emergencies. Cooling a patient to around 20 degrees Celsius, 68 degrees Fahrenheit, slows metabolism and buys time to repair injuries that would otherwise be fatal. Trials are cautious and rare. The aim is minutes or hours of extra operating window, not months. The body is rewarmed promptly and monitored for clotting, inflammation, and organ stress. This is not hibernation. It is a temporary slowdown to bridge a crisis. Outside the lab, a few organizations offer whole body or brain-only preservation after legal death. The process is to cool the body, circulate cryoprotectants, and lower temperature to liquid nitrogen storage. The hope is that future biology, nanotechnology, or other tools may repair damage and reverse preservation. None of this has been shown to work on humans. No person has been cryopreserved and revived. It is a bet on later science, not a current medical service. Turning suspended animation into a practical spaceflight tool would require solutions on 3 fronts. Cooling must avoid ice everywhere, in vessels, organs, and brain tissue. Storage systems must hold stable conditions for years without power losses or leaks. Rewarming and recovery must restore function with memory and identity intact. Even if the technical path existed, questions would remain. What legal status does a person have after decades offline? Who is responsible for care if plans or funding fail? How does a mind adapt to a jump in time? The science is one set of problems. The ethics and logistics are another. The draw is easy to understand. Human lifetimes do not fit well with trips that take many decades. Suspended animation would cut food and water needs, reduce cabin volume, and simplify crew psychology. Until real stasis is solved, crews will rely on robust life support, radiation shielding, and careful pacing rather than a full pause. Far from engineering problems, the solar system itself offers cold worlds where water hides under ice and where energy comes not from sunshine, but from tides. Europa, a moon of Jupiter, shows a bright shell etched with long fractures. Surface temperatures hover around 160 degrees Celsius, 260 degrees Fahrenheit. Radiation from Jupiter is intense at the surface. Beneath the ice, evidence points to a global, salty ocean. Europa flexes as it orbits, squeezed by Jupiter's gravity. That flexing generates heat inside and probably keeps water liquid under kilometers of ice. Hints of fresh surface deposits, variations in magnetic fields, and models of heat flow all support the ocean picture. Enceladus, a small moon of Saturn, is colder at the surface, around 200 degrees Celsius, 328 degrees Fahrenheit, yet more outgoing. Near its south pole, long fractures vent plumes of water vapor, ice grains, and organics hundreds of kilometers into space. A spacecraft can fly through those plumes and sample them, which one mission did. Measurements found salts, simple organics, and tiny silica grains, consistent with hot water interacting with rock at depth. That combination liquid water, chemical energy, and organics points to an ocean beneath the ice, kept warm by tidal flexing. and perhaps by hydrothermal activity on a rocky core. Farther out, Pluto sits in thin sunlight. Average surface temperatures drop to roughly 230 degrees Celsius, 382 degrees Fahrenheit. Despite the cold, images show mountains of water ice, flowing ices of nitrogen and carbon monoxide, and wide plains that look young by crater counts. Bright and dark patches track seasonal cycles as gases freeze and sublimate. There may be liquid layers deep below, insulated by overlying ice and warmed by residual heat from formation and slow radioactive decay. If present, such layers would be kept liquid by pressure and antifreeze effects from dissolved compounds. These environments challenge a simple link between warmth and habitability. Life on Earth adapts to darkness, pressure, salt, and cold. Microbes live in Antarctic ice, in subglacial lakes, and kilometers beneath the ocean in rock. They derive energy from chemical gradients rather than sunlight, oxidizing hydrogen, reducing sulfur, or tapping the redox energy of iron. On an ocean world under ice, tidal heating and rock-water reactions could supply similar gradients. Ice above would shield against radiation. Water currents could circulate nutrients. Cold aids preservation as well. Ices trap organics and gases. Layers record changes over time. If a probe drills or melts through, it may find stratified chemistry that tells a story of energy sources, circulation, and stability. The thickness of the ice, the amount of salt, and the rate of tidal flexing are key numbers because they set heat flow and ocean mixing. Instruments aimed at these questions include ice-penetrating radar, magnetometers to detect induced fields in salty seas, and mass spectrometers to analyze ejected grains and gases. A careful combination can infer ocean depth, salinity, and the presence of vents without touching the water directly. Spacecraft design for these jobs ties back to thermal control. A lander on a frigid surface needs heaters, insulation, and careful schedules to survive long nights. Drills or melt probes must move heat into ice efficiently without boiling away their own coolant. Instruments that sniff faint organics need cold traps and clean lines to avoid contamination. Every watt counts. Power systems balance steady heat for survival against cooling for sensors. The physics that governs a cryostat on Earth governs a probe in the outer system. Energy in, energy out, and the path between. The numbers that look small, temperatures of 10K in dense clouds, 40K for a telescope's optics, 200 degrees Celsius on a moon's surface, drive large differences in behavior. Ices that are brittle at one temperature can flow over geologic time at another. Salts depress freezing points and change how cracks seal. Radiative cooling dominates in vacuum, while conduction rules inside ice. When engineers estimate how fast a plume deposits frost on a lander, or how quickly a drill head cools once power is off, the same equations set the rates. Cryosleep remains an idea in fiction, but cryogenic practice is already part of exploration. Telescopes see best when their instruments are cold. Probes last longest when their temperatures are stable. Samples return in better condition when shipments avoid warm spikes. The discipline that stops ice crystals in a lab is related to the discipline that keeps a detector quiet beyond the asteroid belt. In each case, cold is not just a condition, it is a tool used with care. Europa's crust may be tens of kilometers thick, yet surface features hint at places where it thins or opens. Enceladus vents do the hard work of sampling for us. Pluto's plains refreeze and reform over seasons that last decades. Each case shows that cold does not mean static. It means slow, steady change guided by heat flow, gravity, and composition. Where water persists, chemistry continues. Where rock and water meet, energy flows. Where ice protects, complexity has time to grow. On Europa and Enceladus, 3 ingredients sit in the same place: liquid water under ice, a steady source of heat, and organic chemistry. If hydrothermal vents exist on their seafloors, rocky cracks where hot, mineral-rich water rises, then chemistry could run without sunlight. On Earth, such vents power entire ecosystems. Microbes feed on chemical gradients instead of light, building sugars from carbon dioxide and hydrogen sulfide. Larger animals crowd around them, living off the microbes' work. The idea transfers well. If rock, water, and energy meet below the ice, metabolism has a foothold. We do not know whether vents exist there, but several clues point toward active seafloors. On Enceladus, tiny silica grains found in ejected ice are consistent with hot water reacting with rock. Salts and simple organics in the plumes match an ocean in contact with a rocky core. On Europa, measurements suggest a salty ocean that conducts electricity. Variations in the magnetic field imply deep, mobile water rather than a static block of ice. Surface features ridges, troughs. Possible chaos terrain hint at places where the shell flexes and exchanges material with what lies beneath. To test habitability, missions will map ice thickness, measure composition, and sample material as directly as possible. A spacecraft at Jupiter will perform repeated close passes of Europa, carrying ice-penetrating radar to profile the shell, spectrometers to read surface chemistry, and magnetometers to sense the ocean through induced fields. For Enceladus, designs on the table include orbiters that linger to fly through plumes many times, and landers that collect fresh frost that falls from the jets. Even simple counts of molecules, salts, organics, gases tighten the picture of energy sources and circulation. Pluto, far colder and thinner in sunlight, shows a different lesson. Cold worlds are not static. Images revealed mountains of water ice, moving nitrogen glaciers, and broad, young plains where ices rework the surface. Trace atmospheres freeze out and return with the seasons. Possible slow cryovolcanism reshapes areas with slurries of nitrogen and water. Deep beneath, layers may still be warm enough to stay liquid in places, insulated by thick ice and fed by leftover heat from formation and slow radioactive decay. The physics is patient rather than dramatic, but motion is real. Heat flows, ices creep, and surfaces age and renew. The broader point is that cold does not mean sterile. A lack of sunlight at the surface says little about chemical energy underground. Warmth can come from tides that flex an interior, from radioactivity in rock, or from phase changes as ice forms and melts. Ice shells protect oceans from radiation and hold heat in. Salt lowers freezing points and keeps water mobile. If life needs water, energy, and a suite of elements, many icy moons check those boxes more often than airless rocks closer to the sunday. Such worlds are common around giant planets, and giant planets are common in data from exoplanet surveys. If similar moons exist elsewhere, buried oceans could be widespread. Between these concrete targets and the deep background of space sits an idea with a confusing name: cold dark matter. Dark does not mean dim. It means invisible to light. The stuff neither emits, absorbs, nor reflects electromagnetic radiation, so telescopes do not see it directly. Its presence is inferred from gravity. Stars in galaxies orbit faster than visible matter alone can explain. Hot gas sits bound inside large clusters when it should drift away. Light from distant galaxies bends and distorts as it passes massive structures, revealing more mass than starlight counts. The extra gravity behaves as if something unseen outweighs ordinary matter by a factor of 5 or more. Cold in this context does not mean low thermometer readings. It describes speed in the early universe. Cold dark matter would have moved slowly compared to light when structures began to grow, so it could clump on small scales and seed galaxies and clusters. Hot, dark matter fast, near light speed particles would have smoothed out small clumps and delayed galaxy formation. Warm dark matter sits between the two, allowing some small structures but changing details of how many dwarf galaxies should exist and how dense their centers should be. Simulations that include cold dark matter, gravity, and expanding space produce a web of filaments and voids that matches what large surveys map on the sky. The candidates for dark matter are particles we have not yet captured, weakly interacting massive particles. Once led the list, heavy, slow, and barely touching normal matter. Axions are another option. Very light particles that would act more like a pervasive field and could convert to photons in strong magnetic fields. Sterile neutrinos, cousins of known neutrinos that do not feel the usual weak force, sit in the warm range in some models. Underground detectors wait for a rare recoil as a dark matter particle bumps an atomic nucleus. Space telescopes look for telltale radiation from particle interactions. Colliders search for missing energy events that hint at new particles. So far, results give upper limits rather than detections. The absence of a signal closes off parts of the map, but leaves wide territory open. The accounting helps fix scale. Ordinary matter protons, neutrons, and electrons in stars, planets, and people adds up to only a small slice of the total. Dark matter contributes roughly 5 times that share. The remainder, called dark energy, is the name we give to whatever drives the accelerated expansion of the universe on the largest scales. Dark energy shapes geometry and fate. Dark matter shapes the scaffolding on which visible structures hang. Together, they make most of reality. Yet both are inferred from effects rather than seen directly. Alternatives exist that try to explain galaxy rotation without extra matter by changing the rules of gravity at low accelerations. Such models can match some galaxy curves but struggle with clusters, lensing maps, and the precise pattern of the cosmic microwave background. Observers weigh all the evidence at once: background fluctuations, galaxy clustering, lensing by cosmic webs, and the growth of structure over time. Standing today, the cold dark matter picture remains the best fit across scales, even if the exact particle identity stays open. From the web of galaxies, step back again to long times. Thermodynamics gives the broad arrow. Energy spreads from concentrated forms to diffuse forms. Differences even out. The second law says that in a closed system, entropy, the count of ways energy can be arranged, tends to increase. Stars still shine because gravity has gathered fuel, and pressure holds fusion in their cores. Heat flows outward, and starlight carries energy into space. Over immense spans, gas clouds collapse, stars are born, and stars die. Yet with each step, high-quality energy is converted into lower-quality energy warm radiation that spreads into the background. The phrase heat death labels a limit where useful energy differences fade. It is not an explosion or a sudden drop. It is a long decline in contrast. As fuel for star formation runs out and starlight dwindles, the universe moves toward a state where nothing large-scale changes much because little remains to drive change. In such a far future, most stars would have burned out or cooled into remnants. The leftover glow would be cold, thin radiation near the background. Black holes would dominate the mass ledger for a time, then slowly leak energy by quantum processes on timescales beyond ordinary counting. The endpoint is not hot, it is uniform. All of this ties back to temperature and energy flow. Where energy can fall down a gradient, hot to cold work can be done, structures can form, and cycles can run. Where gradients disappear, motion becomes small and scattered. The cold of interstellar space today sets a baseline for objects far from stars. The cold of buried oceans helps chemistry proceed without being stripped by radiation. The cold in laboratories reveals quantum order by quieting noise. The cold of dark matter is a statement about early speeds that let gravity knit small seeds into galaxies, and the ultimate cold of the distant future is the limit case of a universe that has evened out its accounts. Between these scales, work continues. Instruments tuned to microwaves map slight ripples in the background and fix the universe's age and shape. Spectrographs measure galaxy clustering to trace how structure grows. Detectors in quiet mines watch for rare events. Probes near giant planets count molecules ejected from ice and sniff for signs of chemistry beyond water alone. Thermal engineering keeps sensors cold enough to see faint signals and warm enough to survive the long cruise. If hydrothermal vents do operate under ice, then chemical energy, minerals, and water meet in a place protected from surface hazards. That setting is patient. Reactions can proceed at their own pace, guided by gradients in temperature and composition. If dark matter does anchor galaxies, then gravity had a steady hand in shaping the space where such worlds form. If entropy rules the long view, then the present is a chapter when contrasts still exist and can be used to measure, to move, and to live. The numbers along the way stay small in temperature but large in effect. Tens of Kelvin in a cloud decide whether gas resists collapse or yields to it. A handful of Kelvin in a telescope's camera decides whether a distant glow is detected or lost in noise. Fractions of a Kelvin in a lab let electrons pair and flows persist without loss. The label cold connects them only as a reminder that less random motion often reveals more structure. Where motion quiets, patterns emerge. Where gradients remain, change continues. Galaxies still merge, stars still form, and black holes still feed, because energy imbalances remain. Over very long times, those imbalances fade. The star inventory thins first. Massive stars spend their fuel quickly and die as supernovae, or form black holes in only millions of years. Sun-like stars live billions. The smallest red dwarfs sip fuel so slowly that they can shine for trillions of years, but even they will eventually run out. What remains are remnants, white dwarfs cooling from blue-white to red to dark, neutron stars cooling and slowing, black holes holding what they have captured. White dwarfs are the embers of stars. They start hot and dense, then radiate energy into space. Given enough time, they cool below red glow, becoming black dwarfs' remnants with the same mass, but almost no light. No new fusion restarts in them, because gravity cannot push their atoms close enough to ignite without breaking the quantum pressure that holds them up. Star birth wanes, as gas is locked into remnants or spread too thin to collapse. Galaxies dim as their bright populations fade and their gas supplies deplete or heat. Black holes are not permanent on the longest scales. Quantum mechanics allows a faint glow near their horizons, a process that lets them lose mass through Hawking radiation. The rate is tiny for large holes. Stellar mass black holes take far longer than the current age of the universe to evaporate. Supermassive black holes in galaxy centers take unimaginably longer. Still, the direction is fixed. With time, even the biggest lose mass and eventually disappear. As active engines shut down, what remains is a thin mix of particles and very cold radiation. The expansion of the universe stretches light to longer wavelengths and lower energy. Temperatures approach an extremely low value, a whisper above absolute zero, set only by the most diffuse leftover glow. With no dense gas clouds to collapse, no strong gradients to drive flows, and no compact objects left to power events, there is little work for physics to do beyond slow drift. Heat death is the name for this end state. It does not mean fire. It means no useful differences left to exploit. Thermodynamic equilibrium energy evenly spread removes the possibility of heat flowing from one place to another to perform work. Chemistry needs gradients. Stars need fuel and pressure. Life needs steady energy sources. In a universe at equilibrium, those conditions are absent. What persists is expansion and a sparse, cold bath of particles and low-energy photons. The clock for this story runs far beyond human scales. The last red dwarfs can shine for up to 10, 13 years. White dwarfs cool on scales longer still. The evaporation time for the largest black holes is estimated near 10, 100 years or more. Over such spans, even rare processes accumulate. Orbits change as small kicks add up. Bound systems may unbind, yet these changes lead toward uniformity, not renewed structure. Other endings have been proposed. If gravity were to reverse the expansion, a big crunch could occur. Current measurements point the other way. The expansion accelerates, consistent with a form of energy that does not dilute in the usual way. If that acceleration strengthens with time, a big rip could tear apart galaxies, stars, and even atoms. Observations so far favor a steady, accelerated expansion, which points back to heat death as the default long view. The line from high contrast to low contrast remains set by the second law. Entropy grows in closed systems. On a different frontier, the coldest temperatures do not live in space, but in laboratories where motion is reduced step by careful step, reaching microkelvin, nanokelvin, and below is not a matter of bigger refrigerators. It is a matter of control. Laser cooling pushes against atomic motion by tuning light just below an absorption line. Atoms moving toward the beam absorb photons, and slow, magneto-optical traps use light and magnetic fields to hold and damp motion along 3 axes. Evaporative cooling in magnetic or optical traps then lets the highest energy atoms escape so the remainder settle to a lower temperature. Dilution refrigerators cool solid-state systems by using helium mixtures that absorb heat as they separate into phases at very low temperature. These methods have produced quantum states that act collectively. In a Bose-Einstein condensate, many atoms occupy the same lowest energy state and share a phase. Their matter waves overlap, and the cloud behaves as a single entity with properties that can be shaped by light and fields. In Fermi gases at ultra-low temperature, controlled interactions produce superfluidity with paired particles. revealing analogues of superconductivity in a clean, tunable form. Such platforms let researchers model the behavior of electrons in solids, test how waves and particles interfere, and measure tiny forces. Numbers near the limits are striking. Gases have been cooled to billionths of a Kelvin, above absolute zero. Motion can be so small that a cloud of atoms expands only slowly when released, and interference fringes reveal its wave nature. Reaching these states requires stacking techniques, initial laser cooling, capture in optical molasses, transfer to magnetic or optical traps, careful evaporation, and sometimes adiabatic changes that compress or expand the trap to shift energy without adding heat. Each layer removes a bit more motion while keeping the sample contained and clean. Precision tools grow from this work. Atom interferometers split and recombine matter waves to sense acceleration and rotation with high accuracy. Optical lattice clocks trap atoms in standing waves of light and use ultra-narrow transitions as timing references, reaching stabilities where they can compare time rates at different heights in Earth's gravity. Superconducting circuits cooled to millikelvin serve as low-noise amplifiers and as the building blocks of quantum bits. Each device benefits because cold removes thermal noise, letting small signals stand out. Microgravity extends the reach. In orbit, atoms do not fall out of traps as quickly, so measurements can run longer and with lower disturbance. Facilities on the International Space Station cool atoms and form condensates that persist for times hard to achieve on the ground. Longer freefall and weaker constraints on trap geometry open tests of fundamental principles, such as how quantum matter responds to gravity and whether different atomic species accelerate identically. The path to cold also supports studies far from ultra-cold gases. Cryogenic stages hold infrared detectors for space telescopes far below room temperature, so the instruments do not outshine their targets. Bolometers and other sensors measure faint heat from distant dust and gas, only when their own thermal noise is suppressed. Particle physics experiments operate at low temperature to reduce random vibrations of atoms and crystals, and to separate rare signals from background. The reach into antimatter adds another thread. Trapping antihydrogen requires slowing antiprotons and positrons and confining them without touching ordinary matter. Magnetic traps and cryogenic environments make that possible long enough to compare antimatter's spectral lines to hydrogen's and to test whether antimatter falls like matter in a gravitational field. Cooling here is part of a broader aim to isolate delicate systems and see what differences, if any, exist. Across these efforts, temperature is more than comfort. It is a knob for turning down randomness. Heat is motion. Motion hides small effects. Reduce motion, and weak interactions write clearer signatures into data. Signals that vanish in warm environments become visible when the background is quiet. This is why the last Kelvin, the last millikelvin, and the last microkelvin matter. Each step buys order, coherence, and time. Making and measuring such low temperatures requires different thermometers. At room temperature, a liquid's expansion or a metal's resistance can mark degrees. Near absolute zero, temperature is inferred from spectra, from noise in electronic devices with known energy gaps, from the shape of velocity distributions seen after a trap is switched off, or from the occupation of quantum states whose spacing is set by light fields. Instead of reading a single dial, researchers fit curves and compare to models. Limits reappear here, too. The third law says zero cannot be reached by finite steps. Uncertainty forbids perfect stillness. Practical constraints: heat leaks through wires, radiation from warmer stages, vibrations set floors. Much of the design around low-temperature experiments is quiet work, choosing materials with low thermal conductivity, isolating stages, filtering electrical lines so they do not carry heat, and adding shields that absorb stray radiation. The motives are not records for their own sake. Near absolute zero, phenomena align into simple patterns. Superconductors expel magnetic fields. Their currents persist. Superfluids flow without internal friction. Their vortices come in quantized packets. Condensates support waves and vortices that move in ways described by compact equations. With noise reduced, cause and effect are easier to trace, and comparisons with theory grow sharper. The same logic that cleans up signals on a lab bench shapes how we observe cold places in space. Infrared instruments on telescopes are cooled, so their dark current and thermal emission are lower than the sky they measure. Detectors on cosmic microwave background missions are held near a fraction of a Kelvin to map temperature variations at the level of tens of microkelvin. Shielding and radiators maintain stable environments, so the maps reflect the sky rather than the instrument's drift. In this broader picture, extremes meet. The far future's low contrast is one end of a curve that begins in a hot, dense state. The web of galaxies in between was guided by invisible mass that moved slowly enough to clump. Cold oceans under ice let chemistry proceed in shade. Cold instruments in deep space pull faint signals from the background. Cold laboratories on Earth let quantum order stand up without being shaken apart by random motion. The pursuit of colder states continues because each small drop in temperature can open a new window. Rydberg atoms with huge orbits reveal subtle interactions in tailored light fields. Hybrid systems couple ultra-cold atoms to solid-state devices, blending the control of atomic physics with the scalability of chips. Arrays of trapped ions and neutral atoms simulate models of magnetism and transport that are hard to solve by calculation alone. In every case, success depends on holding energy low and disturbances small, long enough to watch processes evolve step by step. The everyday language we use, hot and cold, covers many scales at once. In space, cold means near the background set by ancient light. In a cloud, cold means tens of Kelvin that let gravity win over pressure. In a telescope, cold means optics near 40 K and detectors much lower. In a lab, cold means millikelvin, microkelvin, and below, where new phases emerge. The direction is the same, toward less random motion, toward clearer structure, and toward longer coherence. Each step toward lower temperature has opened new questions and tools. Cooling is not only about numbers on a dial, it is a method for stripping away noise, so patterns stand out. When motion quiets, symmetry and order become easier to see. Superconductors show zero resistance. Superfluids reveal quantized vortices. Atoms in condensates act with a shared phase. These are experiments in stillness, designed to test simple rules under clean conditions and to build technologies that rely on clarity rather than brute force. Project that logic onto the far horizon of time, and a different kind of stillness appears. Picture a universe in which gradients have flattened and the last bright engines have gone quiet. No new stars take shape because gas is too thin and too warm to collapse. White dwarfs have cooled into dark, inert relics. Neutron stars sit as dense, cold cinders. Black holes, once the final collectors, have leaked away their mass over inconceivably long spans through Hawking radiation. Expansion has stretched all remaining light to wavelengths so long that the background is barely above absolute zero. What persists is a thin mix of particles and low-energy photons spread across an ever larger space. This end state is not a crash or a flameout. It is equilibrium. maximum entropy consistent with the remaining energy and volume. Without temperature differences, heat cannot flow. Without flow, no work can be done. Chemistry needs contrasts to run reactions. Engines need hot and cold reservoirs. Life needs steady input and a place to dump waste heat. When every region has effectively the same energy density, processes slow and stall. The universe is not ruined. It is finished with change of the kind we recognize. The idea invites simple checks. Stars power themselves by moving energy down a gradient from fusion in a hot core to the cold of space. Planets keep atmospheres and climates by trading heat between day and night, tropics and poles, surface and sky. Living cells run on chemical potentials across membranes. Remove the differences and the cycles end. Even schemes that store energy for long spans run into the same rule. The store empties without a refill and without a cooler sink to accept waste heat. Useful work cannot proceed. Speculation sometimes imagines rare events in the deep future, quantum fluctuations, brief local departures from uniformity. The physics that allows tiny fluctuations also says that, on average, they are small and far between. They do not restore the rich gradients that once fed stars and weather and metabolism. The picture remains: a long glide toward uniform temperature, then a near constant background with little to drive large-scale structure. This limit case helps frame the present. Today, the universe is far from equilibrium on many scales. Supernovae enrich gas clouds, galaxies merge, planets shed heat, oceans and atmospheres circulate. Energy gradients abound, and so do opportunities for structure to form and persist. The same thermodynamics that predicts a quiet end explains why there is motion now, because there are still differences to spend. Throughout, cold has served as both subject and instrument. In space, it sets baselines, the 2.7 K bath of the cosmic microwave background in the void, tens of Kelvin inside dense clouds, a few Kelvin for cryogenic telescope stages. On icy moons, cold shells trap oceans and shield chemistry, while tides supply energy below. In spacecraft design, cold is managed with blankets, radiators, and heaters, so sensors see faint signals and electronics survive long nights. In laboratories, cold is engineered so that weak interactions and long-lived coherence can be measured and used. The same language compares all these scenes because they share the same rules. Heat flows from warm to cool. Temperature tracks random motion. Entropy counts arrangements and pulls systems toward states with more ways to be. Gravity compresses and heats. Radiation carries energy away and cools. Materials respond according to structure. Electrons pair in some crystals. Helium flows without friction in narrow channels. Ices creep over geologic time under small stresses when temperatures are right. None of this requires special pleading. Cooling simply lets the weaker terms in the equations matter. It is also why the record-setting chills in the lab are more than stunts. Lowering temperature lengthens coherence times and narrows energy spreads. Sensors read smaller signals. Clocks compare tiny frequency shifts caused by height in a gravitational field. Quantum bits hold states long enough to be corrected and combined. A fractional Kelvin gained by design can make the difference between detection and noise, between a stable instrument and drift. Cold clarifies scale. A drop from 50K to 40K in a telescope stage can cut thermal background sharply. 10 Kelvin in a cloud can decide whether gas collapses or disperses. A few nanokelvin in a trap can determine whether a condensate forms. Each change is small in absolute terms, but large in consequence, because it moves a system across a threshold where one process overtakes another. The thresholds differ: phase transitions in matter, balance points in atmospheres, stability limits in electronics, but the strategy repeats. Control energy flow, reduce disturbance, let structure show itself. Even the distant forecast equilibrium after long expansion fits that framing. It is an extrapolation of the same accounting. As gradients are used and not replaced, contrasts fade. The output of stars becomes background glow. The background stretches and cools with expansion. Engines shut down in order of their fuel and scale. What remains is consistent with the rules that governed the busy past. It is just quieter. Seen together, the frozen places and the cold tools do not suggest emptiness. They suggest focus. In molecular clouds, slow motion lets molecules stick and grow on dust before young stars later warm and remix them. In oceans beneath ice, shade protects chemistry, while rock-water reactions supply energy. In cryostats, suppressed noise exposes quantum order. In deep space, stable cold preserves instruments and records. Each case uses low temperature to allow subtle processes to proceed without being shaken apart. The theme running through these examples is restraint. Rather than forcing systems with high energy, we often learn more by lowering energy until competing effects fall away. That approach has delivered maps of the early universe, spectra of coal, dust, and gas, images of plumes from an ocean world, and phase diagrams of matter near absolute zero. It is a patient method, and it works because nature's rules are steady across scale. Imagine extending that patience to the final, uniform phase. No gradients, no engines, no cycles, only the lasting geometry of space and a thin bath of quanta. Questions remain not about drama, but about meaning at that limit. What is time when nothing macroscopic changes? How do you define a clock when no transition stands out? The answers live in definitions. Time becomes the parameter in the equations that track whatever faint processes remain. Temperature becomes the average energy per degree of freedom of the sparse field. The terms do not disappear, they settle. Cold, then, is not an absence so much as a regime. In that regime, motion is slow, signals are faint, and order has room to appear. It is where we test the smallest forces and the simplest patterns. It is where instruments must be most careful and where models can be most exact. It is also the backdrop that will, in the far future, fill almost all of space. For now, contrasts still abound, and that fact enables everything described along the way. Stars that fuse, oceans that circulate, detectors that see, laboratories that cool and measure. The long arc points toward uniformity, but the present is rich with difference, and difference is what powers change and reveals structure. Cold helps us understand why. Some endings are quiet. In physics, quiet is not emptiness, it is clarity. Lower noise, clearer signal, fewer distractions, surer rules. The same clarity that lets a detector find a faint glow also sketches the far horizon where gradients are gone. Between those points is the landscape we inhabit and study, warm enough for motion, cool enough for structure, variable enough to be interesting, steady enough to be measured. The record books for low temperature will likely be rewritten again, one fraction of a Kelvin at a time. Each advance will tighten a measurement, refine a model, or expose a phase we have not seen before. The map of cold places in the solar system will grow more detailed as instruments improve and missions fly. Together, those efforts make the universe's quiet side legible, from the ices that shelter oceans to the detectors that must not glow, from the gases that collapse at 10 Kelvin to the atoms that share a phase at a billionth of a Kelvin. Seen that way, cold is a teacher. It slows, it steadies, it reveals. And with the noise lowered, the lines of the picture come into focus, a steady outline of matter, energy, and time, drawn with a fine hand, fading gently into the background.